Hello, liquids. Just for you. Liquids. Always a good time. Have a liquid and a solid happening there all at once. Look at that. Ooh, solid and liquid. Just for you. Okay, let's talk about liquids. Liquids are very exciting. Molecules are in constant motion. So there's actually a ton of stuff happening in my water right here. Tons of stuff going on, right? Not as much as would be going on just in the air. So if you look at this coffee cup, yeah, it's a beaker that's also a coffee cup. Of course it is. I got water that's escaping. There's little molecules of water that are like literally pelting me in the face. I can't feel it, but that's actually what's happening. Molecules are in constant motion in liquids, just like gases. If a molecule happens to be near the surface of a liquid, it has enough energy, it can break free of the liquid, and escape. It's escaping. My water molecules are escaping. Right now, that's actually what's happening. My water molecules are escaping. If I leave this beaker cup of water on my desk, probably over the weekend, on Monday, there's not going to be any water in my beaker cup. I'm going to be sad. I'm going to have to get more water. Why? Because they're going to escape. They're slowly, one's going to go, oh, look at that, you can get out. And all of a sudden, it's going to be in the air. Yes, this is what's happening. So they can break free from a liquid state. What is this called? This is actually called vapor. Let me make sure this is in red so you can see it. Vapor. That is what it's called. It is called vapor, and that's what's happening. In an open container, this is called evaporation. Yes, you've heard all these words before. Evaporation. And happens all the time. The liquid state consists of particles in constant motion. Doesn't it sound exhausting? Constant motion. Constant motion. So a lot of stuff is going on. It looks like liquid, like it's just sitting there. It's super busy, actually. If a liquid is in a closed container, this is very exciting. So stay with me here. I'm going to delete all this and I'm going to start writing stuff. In a closed container. So if I put a lid on my beaker cup, let's say it has a lid, because it should, because it's a beaker coffee cup. Let's say it has a lid, okay? If it's in a lid, if a liquid is in a closed container, random motion, because remember we just said that was happening, random motion of the molecules bring them back into the liquid. So my lid. So now random motion. It's evaporation. Evaporation is happening right now. Some of these are going, oh, 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 I'm out. I'm free. And they're in the air. But if I do this, I'm trapping them. I'm trapping them in here. And if I come back on Monday, my water will still be in my beaker coffee cup. So that's what's happening. That's why you need to put, if you want to keep it, you need to put a lid on it. That's why Dutch Brothers sells their cups with a lid. It's not just because I'm a spiller. It's because they don't want the sweet coffee that sometimes comes in here to evaporate out. Because they care about you at Dutch Brothers. Okay, so we're going to focus. We're going to get through this. Okay. Molecules can move from the liquid state to a gaseous state through, what happens? Through evaporation. Yes. Or what else? Evaporation. Or if you want to speed that up, or boiling. So I could just boil this. And then it would all go away. The rate of evaporation is dependent on something we like to call vapor pressure. Vapor pressure of the liquid. So some liquids, as you know, disintegrate quicker. Not disintegrate, they evaporate quicker. So alcohols, for example, not that kind of alcohol. This is Simpson. Acetone is an alcohol. It's in fingernail polish. If you ever leave the thing, boys have no idea what I'm talking about now. I'm just talking to girls for a second. Or you can try this. You take fingernail polish remover. You take the lid off. You leave it off, and it doesn't spill. It will evaporate really quick. Got to put the lid back on. We can play with this in class. I can bring you some acetone or some ethanol or something. It evaporates really quickly because of vapor pressure. Vapor pressure is what's happening. What is the definition of vapor pressure? Let's write it down. Vapor pressure is the partial pressure of vapor molecules in equilibrium with liquid. So basically, how fast is it going to evaporate out of my cup? If I had alcohol in here, not that kind of alcohol, if I had acetone in here, it would, I come back tomorrow, it's gone. I come back in a couple hours, it's gone. Or if I had ethanol or something in here, it would be gone really quickly. But water, it takes a little bit longer for the molecules to leave. Vapor pressure depends on, what does my vapor pressure depend on? Temperature, right? You know this. If I was boiling this, it would leave quicker, right? And what else is it determined? It is determined, because I just said some things have different vapor pressures. So it also is determined by identification of the liquid. So what liquid is it? And what's the temperature? Vapor pressure rises with, okay, just guess this one. Do I really need to write this down for you? No, because you know this, because you're smart. And you can think about, what do you think? Increases with, vapor pressure rises with increasing temperature, right? Obviously, you boil something, it's going to evaporate quicker. The boiling point of a liquid is the temperature at which the vapor pressure, vapor pressure is equals atmospheric pressure. Is the temperature. Okay, let's put that in red so you can see it. And let's spell atmosphere right. What do you say? The temperature at which the vapor pressure equals atmospheric pressure. That is the boiling point. That's when the thing boils. Okay. When is the vapor pressure equal? When the vapor pressure is equal to the vapor pressure. All right, vapor pressure is equal to the atmospheric pressure. I just said that. We'll put it again. Atmospheric pressure. I can't spell. Okay, atmospheric pressure. And again, I cannot spell atmospheric. I do not know what's going on. Okay. There you go. Normal boiling point is the boiling point at, sorry, it's not in red, and I know it should be, at a pressure of exactly 1 atmosphere. So if it's boiling, it's at 1 atmosphere. 1 atmosphere. Okay. So I think we've talked about that. We get it, right? Boiling point, atmospheric pressure. We get that. Molecules are moving around. Not as fast as in a gas, right? This is not gas, this is liquids. We've slowed them down a little bit, but they're still moving around and things escape. And we can make that happen quicker by raising the temperature, and they happen differently in different elements. Okay, viscosity, let's talk about that. The measure of a liquid's resistance to flow. So what does that mean? Something is viscous, a viscous liquid, you've heard this used. It means it pours slow. It's like syrup or honey. It's viscous. It's like you pour it and it's blah, blah, blah. Sometimes ketchup, you're like eat on the bottom of it trying to get it out. It's viscous. Or it just the measure of liquid's resistance to flow. Water flows pretty easily, right? I could dump this out all over my desk, which I won't do, and you won't notice. It's very viscous. Viscosity increases with, let's guess. Viscosity increases with intermolecular forces. Remember those? Intermolecular forces. Remember dipole, London dispersion, hydrogen bonding? All intermolecular forces. Okay, so surface tension is caused by the difference between. So let's talk about surface tension. And the purpose of this was I was going to try and float a paperclip on the top of my water. But A, I don't have that kind of paperclip, and B, you couldn't see it. I would have to move the camera and it wouldn't work. But just trust me, paperclips will float on top of water. You can make this happen, right? You know what happened. Surfboards. Think of a surfboard, tiny surfboard in my water, right? This is surface tension. What is this? What is happening? Why is surfing even possible? Because of surface tension. Surface tension is caused by the difference between the intermolecular forces. Oh, not red. I do not know why I will not said intermolecular forces experienced by molecules at the surface of the liquid and those experienced by the interior. So what this means is the surface of my water, the top of this water, you're going to experience something different than if you're down here. So what does this mean? You can slap the water. If you've ever belly flopped off a high dive, you've experienced surface tension. This same doesn't happen. Like, you can float in the water. Once you're down, it's all good and it's not painful. But if you go down on the high dive, right? Everybody's done it, or at least you've seen a kid do it, and you're like, ooh, and it hurts, and it hurts you just to see the kid do it. Surface tension. That's intermolecular forces. They're different at the surface. And you get surface tension. Okay, water is so cool. I just cannot even tell you how cool it is. It's so, so cool. It covers 71% of the Earth's surface. It makes up 60% of the mass of your body. Water has unusual properties, and all of them are incredibly cool, and I could talk about them all day, but I don't have that much time, so you don't get to. First, it has a high specific heat. Specific heat. What does this mean? It means it doesn't readily change temperature. You're like, what are you talking about? It doesn't. This is why it may, I'm not saying it is, I'm saying it may be cooler to live in San Francisco. It may be cooler to live in San Diego. It may be that bunches of people want to live on the coast of California, and not everybody wants to live in Redding. I know that's crazy. It's only because they don't live here and because they like airports. So why is this? Why is this happening? Because the temperature is constant, right? It's kind of depressing. You're like, what? It's kind of always 70 degrees in San Diego and it's sunny. Why? Longitude, latitude, we're kind of close to some of those places, and yet our temperature is very different. Why is that? Because high specific heat. It holds the heat. It keeps the temperature from not fluctuating a ton. You know why this is awesome? If you even don't live in San Francisco, it's awesome if you're fish. It's awesome because you're like, your house isn't like rapidly changing temperature every day. So you stay up, your fish house ocean stays a constant temperature. This is super important. So one of the really great properties is you have a high specific heat. That means it takes a lot of energy to change the heat back and forth. What is the other one? It has a high surface tension. So this is not so good if you're a little kid jumping off the high dive onto your stomach. This is painful. But it's super great for other things. It's super good for those little water striders that get to crawl across water. It has a high, high surface tension. And once we get to physiology and biochem, we'll talk about why this is awesome. I promise we will talk about why this is awesome. Okay, the last one. It has a high boiling point. Most of these unusual properties are related to hydrogen bonding. Remember, I said, if you need to guess hydrogen bonds. Why does ice float? This is important. Liquid water. I'm going to ask you this on a quiz. Liquid water is denser than solid water. You know why else this is great if you're a fish? Because the water freezes down. So if you're a fish who's living in my cup, because that would be fun if you're a fish, this part of the cup is going to freeze over in the cold, not in Redding, but in North Dakota. It's going to freeze over from the top down. If it froze it would freeze you as a little fish, but it goes from the top down. Thus, it insulates you and keeps you warm. This is really important and really, really awesome. Okay, that, my friends, is liquids. Go have some liquid, and then we'll talk about solids.